afternoon and welcome to this Colt CPD seminar on pressurization systems. This seminar is part of a series of CPD-accredited seminars that Colt carry out, the list of which can be seen on the right-hand side. A recording will be available after the presentation, and an email with a link for CPD certificate will be sent to everyone who is attending the seminar. There will also be a question and answer session at the end of the seminar, when we will respond to as many questions as we can. For those of you who aren't familiar with Colt, Colt is a company that was founded in 1931 and in the UK in 2019 had a turnover of 38 million and a group turnover of 180 million. We have manufacturing facilities in UK, Holland and Germany, and accreditation with a wide variety of industry bodies and associations. Colt has been a family-owned company since its founding until recently when it joined the Kingspan Group. We are active in a number of fields, as can be seen here, from smoke control, where we're able to provide smoke and heat exhaust ventilation systems, car park ventilation, smoke containment, typically smoke curtains or fire curtains, smoke shaft systems and pressurization systems, which we'll be talking about today. We are also involved in climate control, providing ventilation systems to deal with overheating in factories and other commercial and industrial buildings, including the use of evaporative cooling, about which there is a separate seminar. We also do louver systems, which are performance-based louver systems, providing sort of screening or more commonly sort of ventilation and rain defense. Plus, we also deal with acoustic and shading louver. And finally, service. An important aspect of any fire safety system is that the system is maintained to ensure that it's operating at all required times. But now we move on to the subject of today, which is pressurization systems. And the first question that we should ask is, why should we pressurize? Approved document B to the building regulations basically requires that smoke ventilation is provided to escape stairs in residential buildings, and under most circumstances, the adjacent common lobbies and corridors, and also to firefighting stairs in all types of buildings. And pressurization is one way of meeting these. There are alternatives that are given here, and in recent times, it's fair to say that sort of pressurization, the popularity of it has declined. Other systems have been developed, but we have noticed certainly that there is something of a comeback in its popularity. It can be used as an alternative to natural ventilation when stairs are landlocked, but as it's noted sort of here, sort of the BRE shaft and the Colt shaft have significantly reduced this market, but as I say, it is coming back. It's a requirement for some firefighting stairs, and it can be used as a method of discounting a stair in some buildings. Pressurization systems should conform to the requirements of EN 12101 Part 6, which is a standard that forms part of the smoke and heat control system EN 12101 range of standards that covers many aspects of smoke management systems in buildings and the products that are associated with it. If we take BS 9999 as an example, then that recommends pressurization to avoid discounting a stair and the sizing of escape stairs. It allows stairs to extend down to basements, and it should be used to protect firefighting shafts that are over 10 meters deep or 30 meters tall. So there's a number of areas sort of where pressurization can be used, either because it's a requirement or because it enables you to discount some other fire safety measure within the building. Colt have a wide variety of experience in providing pressurization systems in buildings such as offices and residential buildings, in buildings with basements and hotels. In order to design a pressurization system, we need to understand exactly what it is that it's intended to do. And there's a variety of classes which dictate sort of the level of protection that's required. And the class relates to the sort of risk associated with it. The most basic is Class A, which is a means of escape system, which is used in residential buildings where a stay-put policy is being implemented. Class B is used for means of escape and firefighting, and for buildings where there is a firefighting core which needs to be provided with protection, and this is a method that's to be used. Class B tend to be the most onerous sort of requirement. The reason being in that because it's there to protect firefighters, then obviously it needs to provide protection, when quite possibly the fire is more intense, and so the level of protection that's required is that much greater. Other classes are Class C, which is means of escape for simultaneous evacuation, which is typically commercial buildings. And then you have classes D and E, which cover sleeping risk and phased evacuation. And it would be fair to say it's not as common as the other classes. There are also other classes if you actually look in EM 12101 Part 6, but those relate to sort of requirements of some European countries that don't tend to get used in the UK. The basic principle of pressurization systems is that the system must protect against smoke entering the stairs or travelling between stories via lift lobbies or protected corridors. And the intent is that basically what we do is we provide the highest pressure in the stairs and a reducing pressure gradient, sort of travelling away from it, so the airflow is always from the stairs away to the accommodation. The accommodation sort of in pressure up when talking about pressurization is defined as any space outside the protected area. So, for example, it could be an office area, it could be a corridor coming up a stair that's being pressurized, but it's any point that isn't part of the actual pressurization system that isn't actually being pressurized by the system. And when we talk about pressures, what we're talking about is the pressure differential between the place that we're looking to protect, be it a stair, lift or lobby, and that accommodation. So the accommodation is always a reference point of zero, and pressure should be measured relative to that, not to outside or anything like that. When we look at a pressurization system, there's three basic components. We need a means of getting clean air into the pressurized areas. We need to look at a means of ensuring that excessive pressure differentials don't occur, which we'll come on and talk about a bit later, and a means of getting rid of the relieving pressure from the accommodation. As we'll see, it's important that with a pressurization system, there's a means of ensuring that the space outside the pressurized areas, the pressure can't build up in those areas, otherwise the pressurization system doesn't work. So the first decision that we need to make with any pressurization system depends upon what the class of the pressurization is, and it depends upon building layout. So we need to ask ourselves a question of sort of, for example, where is there a lift? Where is it suitable for accommodation air release? And there are a number of sort of things that we can do. If, for example, we take a simple stair, then we can pressurize the stair. And if the lobby is simple outside and we don't need to pressurize it, then we can provide our accommodation air relief from that space. And that accommodation air relief is there to ensure that we don't get the build-up of pressure within that lobby, as shown on this sort of drawing. And also, when we come to achieve sort of open door velocities, then the air can continue to flow through the door into the lobby area so that we maintain the design conditions. In some instances, we pressurize the lobby as well. Typically, sort of by doing this, we can protect this area, and it also prevents smoke flowing through the lift from floor to floor. Or we can just pressurize the lift, which basically has the same effect in that sort of the smoke can't get into the lift, but it doesn't protect the areas outside the stairs or outside the lift. Or when we look at firefighting systems, which are Class B systems, then in those situations, we pressurize all three. So we pressurize the lift, lobby, and stairs. And what we would typically do is pressurize the stairs and lift so that they are at slightly higher pressure than the lobby, which is obviously at a higher pressure than the accommodation. And as you can see, that will always ensure that the airflow is from the stairs and lift into the lobby, and then from the lobby into the accommodation. So the air is always flowing in the right direction, and it prevents the smoke actually entering into the lobby and hence the lift and stairs. So we are always protecting the stairs. There's three set criteria that we have to achieve with any pressurization system. Firstly, we have to achieve the required pressure differentials, typically when all the doors are shut, although in some instances when one or more doors might be open. Then we have to achieve certain velocities through open doors. And we also have to make sure that we limit door opening forces to ensure that sort of people aren't sort of trapped within spaces because of the build up of pressure within the spaces, which is why sort of there's certain sort of limits on the pressures that we achieve. And if we take a look at a Class A system, then this very simple sort of schematic shows what it is that we're trying to achieve. When all the doors are closed, for this Class A system, we pressurize the stairs to 50 pascals when all the doors are closed. In the fire condition, the automatic air release is open and the pressure relief damper would be operating. Now, the pressure relief damper is an essential part of the system because it's the means by which we ensure that the pressure doesn't exceed 50 pascals. When we come on and look at the open door condition, we can see that we require a velocity through that open door of 0.75 meters per second for a Class A system. Now, firstly, in order to achieve that, that airflow going out that door needs to go somewhere, which is why the accommodation air release ventilator is important, because that allows the air to flow out continually. If we didn't have that when we opened the door, all that happened is that that lobby that's shown the pressure would build up in that. We'd get pressure equalization, and we wouldn't actually get any airflow from the stairs into that lobby. The other criteria that we have is that because the airflow that we might need into the stairs in order to maintain that velocity is greater than what we require in order to pressurize the stairs to 50 pascals, we have a difference in the requirement in the two conditions. And this is where the pressure relief damper comes into the system, because that is the means whereby we can, as the name implies, we can relieve the excess air that we don't need so that we can maintain 50 pascals when the doors are shut, but when the doors are open, we can then maintain the open door velocity. Pressure relief dampers can take a sort of variety of can be achieved through a variety of methods. We found it effective to use dampers similar to those used in hospitals, which are sort of specially weighted dampers, which have a very sort of specific performance curve in them, so that they don't open sort of as soon as you start applying pressure to them. Class A systems, which are used in residential buildings, sort of the first and foremost, the thing that you don't do is you don't take pressurization up to the front door of dwellings. In order to do that, you need to sort of achieve the open door velocity across the front door of the dwelling. And so it means that you need to ensure that there's an accommodation air relief path actually inside the dwelling, which is difficult to achieve. And also it's very difficult to ensure that it is maintained operating at all available times. If we don't have that, and obviously, if someone decides that they don't like the look of the grill or whatever it may be that they've got within their dwelling, and they sort of put a rug or a picture over it, then it's going to effectively it's going to make the system sort of ineffective in the event of it being a fire in that location. So generally speaking, sort of whenever we do pressurization systems in residential buildings, then we look to provide the accommodation air release from the corridor or the lobby, because that tends to be under sort of management control. If we have long corridors with smoke seals, with smoke-sealed doors, then the air release needs to sort of take into account that these doors and basically sort of be on the right side of the door to ensure that it's going to work, as is shown here. So it's important that we are providing the accommodation air relief from the space outside from the area outside the space that's being pressurized. And the air does not have to pass through additional doors in order to get to it. When we come to Class B systems, then the requirements are set by ADB and BS 9999. And with Class B systems, firefighting stairs, pressurized lobbies are essential, because it's the point at which the fire brigade sort of will group and sort of start approach to attack the fire. So it's important that they're protected within that space. If the lobby contains a firefighting lift, then that also needs to be pressurized. And this is a typical schematic of a Class B system when all the doors are closed. And you'll see that there's sort of many of the same elements that we had with the Class A system. The only addition at this stage being that you can see that the lobbies are shown. If there is a lift, then that would also sort of be pressurized to 50 pascals, but it's just missing from this representation because otherwise it just gets a little bit confusing. But the basic criteria are the same. The difference comes when we look at the open door condition, because the velocities are considerably higher. It is considered that sort of the pressure doesn't need to be any more than 50 pascals in order to hold the smoke back when all the doors are closed. But in the open door condition, because the fire brigade are going to be dealing with the fire when, as I said previously, it's like to be much more developed, then the velocity across the door into the accommodation needs to be considerably higher. So rather than our 0.75 meters per second that we mentioned earlier, we're now talking about a velocity of 2 meters per second. And so everything tends to get sort of significantly larger. Not only sort of do we have to achieve it when a velocity of 2 meters per second, but you'll also notice sort of down in the bottom left-hand corner of the figure that the final exit door is open into the stairs. And these doors which are open have been dictated because of the way that the fire brigade would typically approach a fire, and the way they would, for example, run their hoses and how they would use the lift up to the floor below the fire and then open door and then approach the fire floor via the stairs and then form their bridgehead in the lobby and then sort of tackle the fire from that point. But the basic thing is the same. The only thing is that, of course, because the door to the base of the stairs is typically open directly to outside, then we do have an awful lot of air that is just leaking out direct to outside when we're trying to maintain our 2 meters per second velocity up on the fire floor. So it does mean that the volumes volume flow of air that we require does go up quite significantly. When we look at Class C systems, then with the door closed, it's identical to the Class A system. But with Class C systems, there is an additional requirement that when the final exit door is open, we have to still maintain a pressure differential of 10 pascals within these stairs above the accommodation on the fire floor. So again, this causes the sort of duty required for the system to be sort of larger than a Class A system, because we have to deal with this sort of leakage through the final exit door because we're sort of pressurizing the stairs to 10 pascals. In the open door condition, with the door open on the fire floor, that open door condition, as you can see, sort of the system is very similar, or is identical to the Class A system. So the only difference between a Class A and a Class C system is the 10 pascal requirement when the final exit door is open. This gives a summary of the requirements of each of the different classes of system. As you can see, we've spoken about sort of Class A, B, and C. And so we have our 50 pascals, 0.75 meters per second, and 2 meters per second velocities. And you can see that for classes D and D, the basic requirements are very similar. It's just that depending upon whether it's D or E, then it's just the number of doors in certain circumstances, sort of the number of doors that are open sort of vary depending upon the different scenarios. You'll also see that there's a note there that pressurizing sort of whether or not we pressurize the lift space, the lift shaft, or the lobby in some instances is at the discretion of the system designer, and that is something that should be agreed at an early stage so that everyone understands exactly what it is that the system is being designed to protect. When we come and look at what equipment we actually need to achieve the performance requirements, then firstly we have the fans, which are typically sort of duty and standby, which can be in series, duty and standby fans in series, or it can be sort of a duty and standby one fan with two motors. Typically, sort of we use one fan set to pressurize everywhere. So, for example, if we are doing a firefighting stair and we're pressurizing the stairs, lobbies, and lift, then we would use one fan set to pressurize all three. They're not normally attenuated unless they're needed for test periods. And one important thing about them is that they should be ambient rated. They don't need to be smoke extract fans. They're designed to push fresh air into the spaces that we're looking to protect, not smoke. And indeed, I would say that it'd be detrimental if you did use smoke extract fans, because that means that if for any reason any smoke did get into the system, then the system would sort of keep running and keep pushing smoke into the space. So they should always be ambient rated fans, and they either go on the roof or they typically go in a 1 hour fire rated enclosure. For power supplies, then we should have them, as you would expect with any life safety system. We should have sort of primary and secondary or mains and generator back power supplies. As I mentioned, sort of pressure relief sort of is the method whereby we sort of maintain pressures and deal with the difference in airflow requirements for the open and closed door conditions. And typically this is dealt with by using a gravity damper located in the stairs, or we can use inverter control. But When we have used inverters on their own in the past, we have found it difficult to actually get the response time needed to ensure that when we close the doors, then the fans can slow down quickly enough. It's a much more effective method is to use a gravity damper, and as I say, these are readily available and are a much more effective method of actually sort of controlling and regulating the pressure within the stairs. When we come to ductwork, then typically where we have one fan set on the roof, then we separate the ductwork at roof level. So we have separate supplies, but separate vertical ducts running down to stairs, lobbies, and the lift shaft. The ductwork doesn't need to be fire rated. It can be ambient rated ductwork, unless, of course, it's breaching the fire compartmentation, in which case, of course, it needs to be fire rated. Builders' work shafts are totally suitable as long as they're well sealed. And, of course, if the builder's work shaft actually opens, is actually connected to the space that you're pressurizing, then if it does leak, the only place it's going to leak is into the place that you're pressurizing anyway. So they are perfectly sort of acceptable for use. It's important that there's means of adjusting the system. When we come on and talk about it, we will see that sort of with the calculations, we have to make assumptions about how well the building's going to be built and how well sealed it's going to be. Now, that is the one thing that it's virtually impossible to quantify until you actually get on site and sort of start running the systems. So it's important that there's means of sort of balancing the system using VCDs at T's and at grills so that we can sort of make fine adjustments to the system in order to achieve the required performance criteria. If we're putting our fans on the roof and we're drawing air at roof level, then it's important that we have two separate inlets which are well spaced apart and facing different directions, and have smoke detectors located sort of in the duct just inside each of these inlet points. And this is very simply because if we have a fire within a building, the smoke's obviously going to, and it gets out of the building, the smoke's going to sort of rise up the side of the building, and it's quite possible that one of those inlets could be affected by smoke. So that can be picked up by the smoke detection. It can close that inlet and open the other one. That's not a requirement if the fans are located at ground floor level, obviously, because they're not likely to be affected by rising smoke. It's important that we get good air distribution in each of the spaces that we're pressurizing. So when we consider the stairs, for example, if we just had one inlet point in a stair that was 50 meters tall, then what we would find is a significant pressure gradient down the length or down the height of the stairs. So whilst we might be setting it so we get 50 pascals at the top, we could get considerably less at the bottom. So it's important that we have well-distributed air. And the standard requires that we have one for every 3 stories in the stairs. If we're going to pressurize each lobby as well, then we need one for each lobby. And with the lift shaft, the recommendation is that we have one per 30 meters in the lift shaft. So if the lift shaft is less than 30 meters tall, then we can just have a single inlet point. If it's above that, then we start needing more than one, depending upon the overall height of the stairs. Here you can see on the left-hand side an example of sort of the 2 inlet points facing in 2 directions, and these are about 5 meters apart. So they're considered to be sort of unlikely to be affected by, or both of them to be affected by smoke at the same time. And on the right-hand side, you can see that there's volume control dampers fitted to actually enable us to balance the system so that it achieves the design criteria. When we talk about accommodation air release, then there's, again, a number of ways that it can be done. You can rely on leakage from the building fabric. but in doing so, it's unusual that you'll get, certainly in a modern building, sufficient leakage to ensure that you actually can achieve the design condition. You can't rely on window breakage sort of occurring during the fire. The system must be able to perform even in a non-fire situation so that it can be tested and demonstrated to actually perform as required. So typically you do need to have some identified means of providing accommodation air relief. You can use 2 windows, or you can use windows. But if you use windows, then in order to minimize the effect of wind, then you need to have windows on 2 different sides, and you discount the side with the largest window area if they're different sizes. And the size of the windows, which would need to be based on a velocity of sort of 2 meters per second. An alternative is to use a natural shaft running up through the building. So you have dampers on each floor, and you open the damper on the fire floor, and the accommodation air relief path then becomes sort of into the shaft, rising up to the shaft and discharging out through the top. One of the things when you start using natural shafts can be sort of the additional resistance that you get within the shaft can put a greater demand on the system and rely on a greater volume flow. So the most effective method of doing it is to use windows wherever possible. You can also use mechanical shafts. You mechanically extract the accommodation air relief. But with using mechanical shafts, you have to take measures in order to prevent there being excess pressure differentials when all the doors are closed, because if your mechanical shafts are extracting from the area outside the pressurized space, when all the doors are closed, it can cause a negative pressure outside, and so you can end up with sort of excess pressure differentials between the pressurized space and outside. Any pressurization system should be initiated from a fire alarm system, and in order to ensure that the accommodation air relief only opens on the fire floor, then the system needs to be able to identify the fire floor, typically by using detectors located close to the door to the pressurized space. With Class B systems, if you don't want it running in Class B mode sort of as soon as the fire starts, then you can have switches to change from the means of escape state to the Class B system. But generally speaking, sort of because it doesn't put any additional sort of pressures on the door, then there's no real need, and sort of most systems start automatically as Class B systems from the outset. As I've said, accommodation air relief sort of should only open on the fire floor to prevent the risk of smoke or fire spread to other floors, and firefighters should be provided with a means of controlling the system at the base of the stairs. Now, the basic principle of pressurization is very simple and can be compared to, and a good analogy is if we pump air into a ball or a tire, then the tire or the ball inflates because we have a positive pressure inside. And if we have a puncture in our ball or tire, then we need to keep pumping air in order to maintain that ball or tire at the pressure. And if we know sort of how big the hole is in the ball or the tire, and we know what pressure we want to achieve, and we want to sort of maintain that pressure, then basically we've got a fixed rate of air input to balance out the air that's leaking out and maintain the pressure. Fortunately, thanks to Bernoulli, then there's calculations that we can do in order to determine if we have a space and we know how much leakage, or we can estimate how much leakage there is, then we can calculate the volume and flow of air that we need into the space in order to maintain that pressure. it does sound easy in principle, but when we start looking at some of the flow patterns and we start flowing through sort of multiple openings, then it can become slightly more complex. Indeed, EM 12101 Part 6 does actually have a 12-page annex to this, which covers all the sort of various calculations. But in the end, sort of what we get, if we go through sort of all the various calculations, unfortunately, we don't always need to use all 12 pages, is we end up with a closed door total airflow, an open door total airflow, and an airflow in order to achieve the 10 pascals for Class C, D, and E systems, and the pressure and the airflow out through the pressure relief vent, damper, shaft, whatever it may be. When we come to designing the ductwork for the system, then it's just done in the normal way. Sort of, if we know the duct layout and we know the size of it, then we can calculate the pressure drop at all the various components, and we can add them all up and we come up with a total pressure for the system. But then, of course, we have to remember to add on the actual operating pressure of the system, something which is more forgotten more often than it probably should be, to add on that extra 50 pascals at the end to allow for the fact that we are going to pump out the space to that pressure. And now we come on to problems. Unfortunately, sort of pressurization has at times had a bad press. Some people think it is sort of slightly more complicated than it should be. Pressurization systems sort of generally sort of fail or don't work as they should because the structure is leakier than was allowed for, which is either because the designer hadn't allowed for the actual building leakage that's present, or it hasn't built to a high enough level of construction. Good liaison and speaking to the architect and builder is important in order to ensure that the structure is sealed to an acceptable level, to avoid the need to go back and sort of test. Perhaps it was best put by an architect who said to me sort of a few years ago that sort of when you're building a staircase, then you might normally build a mini, but if you're building a pressurized staircase and you need to build a Rolls Royce, might be a slight exaggeration, but it certainly needs to pay much more attention to detail of the ceiling, or it can just cause problems further down the line. So when we look at the design and when we look at the design process, it's easier to see why these problems can occur if they're not sort of dealt with properly. Because when we do make an assessment of what the build quality is going to be, it does become something of a guess. If we look in EM 12101 Part 6, then it just gives three definitions of construction as loose, average, or tight. It doesn't actually tell you what loose, average, or tight means, so it becomes sort of open to the interpretation of the designer. So it's important that in order to sort of minimise problems, that a good assessment is done and the most appropriate sort of selection is made at the time. As you can see, sort of we do add on a number of safety margins are added on, sort of allowing for unidentified leakage, sort of duct leakage, pressure losses, and these can be important because if we reduce them, because we think sort of we can maybe sort of get away with a slightly smaller plant, then it can lead to problems at completion because the pressures or velocities can't be achieved. So it's important, but the important thing is to understand the process of what it is you're trying to do and the actual sort of concept of it, because that enables you to be sort of much more appropriate and much more project specific in your design. And when we come to commissioning, there's a process obviously that we follow. And commissioning is important because obviously we have very prescriptive sort of criteria that we have to achieve. For example, if we take the firefighting stair, then the average velocity needs to be 2 meters per second. The pressure has to be 50 pascals, so it becomes very straightforward. Does it or doesn't it? Yes or no, and it becomes sort of a pass or fail. So when we sort of go through the process, then sort of we obviously have our sort of checks that we do, as you can see there. And we make sure that sort of everything is sort of working and all the equipment is sort of doing what it should be and all the right things are in place. In particular, for example, sort of, we don't particularly want smoke seals on doors. On doors, sort of it's important that all doors must be fitted and closed properly. And another aspect is sort of looking at finishes. Sort of, there's no point going in and commissioning a pressurized stair if, for example, it's bare concrete and you're going to come along and put in carpets, because when we look at the gaps under doors, well, before the carpet's laid, we might have a gap of 20 or 25 millimeters, and then someone comes in and puts a really thick carpet in and closes that gap down from 20 millimeters down to sort of like 3 millimeters, and that has a significant effect on the pressures that you're going to be recording in each of the spaces. So it's important that the building must be as finished as it possibly can be. And if you are trying to commission it and there aren't, and the carpets aren't there, but they're going in, then it can not be a bad idea to find a couple of carpet tiles and just put them underneath the door so that you fill the gap to something close to what it will be when you actually come to finally commission it. When we come to test the system, then because it's a building and because the wind is going to be blown around it, then it does have an effect on the readings that you get. So where possible, then sort of very windy and especially blustery days should be avoided, because otherwise it will give fluctuations in the results. But when we look at sort of the performance, then basically sort of everything should be done so that there's no gap of more than 15 minutes between test stages to ensure that we've got consistency of testing. And obviously everything else has to be shut down. Measuring sort of pressure differentials is very simple, sort of using a manometer and 2 long flexible tubes. Then you can pass one end of the tube either under the door, or if there's any openings that are specifically designed, then you can use that. And then basically you read the pressure differential across the door. Here it's showing reading a pressure of 51 pascals. And then for the open door velocity, then we open the door and standing away to one side of the door, out of the airstream, and basically using a rotary rain anemometer or something similar, then we can measure velocity at 8 points, and the door velocity that we're interested in is the arithmetic average of those 8 readings. When we're measuring pressure, then basically we do it on each floor in turn, and we open and close the doors, and then we measure the pressure differential when the doors are closed. And it's also important to measure the door opening force as well, using by the door handle. And similarly, sort of with velocities, we measure on each floor in turn as well, if it's necessary. As it says at the bottom, it says a very simple line, sort of adjust system as necessary and retest until all pressures and velocities are correct. Obviously, sort of quite how much adjustment is needed. Sounds very simple, but excessive leakage, as said here, sort of can lead to issues of commissioning and sort of multiple visits, and also sort of it can take time to sort of test and balance these systems, especially when you have lobbies. But again, it all comes down to the knowledge of the designer to ensure that the system is designed so that these problems can be minimized and the system can be commissioned in as few visits as possible. So the summary of sort of what we've been through is first to say, do you need pressurization? Once you've decided on that, then it's identifying what class of systems needed, decide what areas you need to pressurize. Is it the stairs? Is it the lift? Is it the lobby? Select the accommodation air relief method, calculate the flows, select the equipment, and install and commission it. And then once we've done all that, and obviously it's important that the system is tested regularly and maintained to ensure that it will perform as it should do throughout its life. That brings us to the end of this seminar. We'll now take a short break while we sort of have a look at any questions that we may have had, and we will come back to you shortly where we'll hopefully be able to answer some of the questions that have been asked. Thank you.